Very good day to everyone. We Group 1 today will be presenting the computational chemistry challenges. DFA B3LEAP is the most widely used and extremely popular as it has conceived 25 years ago. B3LEAP has achieved a new level of accuracy at affordable computational costs. We forecasted in 2043, the computational possibility depend on the future development of software as well as computer hardware. Thus, it will be more difficult to predict its development of special large-scale consumer hardware, especially graphical processing units, as they are more likely to develop faster due to continuing demand in visualization of all kinds. Hence, we have a doubt here on can the algorithm and computational chemistry computers codes keep pace with such development, as they are not driven by a large workforce nor an entrepreneurial spirit. In the optimistic scenario, an energy evaluation would be completed in only 1 millisecond, and the entire structure optimization will only take 0.1 seconds. This fast field speed would open the heaven of routine for full ab initio MD treatments, large-scale conformational searches, and screening application of chemically large systems within minutes. In a more realistic scenario, the geometry optimization will only take 2 minutes, but the MD will still run for days, indicating we must further develop quantum chemicals methods and algorithms instead of relying on software. The field of theoretical spectroscopy that has advanced remarkably in recent years is not considered as the methods are very diverse and their development even less predictable.
Hi, I'm Juetian Janice. I will discuss about the low-cost quantum chemistry method will replace the force field. Force field method was extensively used by chemists, and the last force field used is MM3. Currently, conformational searches are conducted at the semi-empirical molecular orbital (SMO) theory or low cost at DFT level. The introduction of DFT-derived type binding methods, which is DFTB, was in the early 2000s. DFTB inherits some of the desirable quantities of DFT. It is also applicable to most of the elements that up to Z equal to axis of the periodic table in a modified and dispersion corrected form. Reactive force fields lack of the proper physics and are likely to be replaced in the future. For example, tight binding SMO method that can be properly dissociate covalent and other bonds will replace the reactive force field. However, polarizable force field, which is still non-standard, are likely to survive for large biological systems with greater than 10,000 of atoms. Classical potential may be used in the future for the interpolation of potential energy surface through an on-the-fly force field generation. Embedding theory, which is another modern and promising research direction for methods with intermediate accuracy for larger systems, naturally couples the system of fragments of different size and chemical importance of quantum mechanically.
Hello and good day everyone. My name is Tang Miqian. I will continue the challenge of computational chemistry in DFT and WFT. DFT is the density functional theory which is lacks in the systematic improvability and have self-interaction error. In the model of H2 and H2 plus dissociation curve, which are never both correct for a given density functional, it will always only one of the two molecules can be described well, while the other is in error. By solving this problem, it will strongly contribute to the desired increased robustness of DFT methods. Therefore, the development of mostly empirical functional should not only concentrate on the chemical energy, but in addition consider their robustness or numerical stability. On the other hand, about the wave function theory, it is practically problematic for large or strongly correlated systems. It also shows a slow convergence of the result with respect to the quality of one particular system. Next, the basic set problem in quantum chemistry was hoped to be practically solved so that we can soon write an arbitrary. In the study of full CI methods, which are necessary to describe complicated and strongly correlated systems like metals, is still unclear and more study are needed. I will pass the presentation to another presenter.
Hi, my name is Yo Ying Xun, and I will be talking about entropy and nuclear dynamics will be included accurately and also routinely. A large system have many electrons and also nuclei. In traditional quantum chemistry, it only focuses on electron quantum property or small nuclei system, but very many nuclear degree of freedom are ignored by the Born-Oppenheimer approximation. A process like tunneling and also accurate spectroscopy are required consideration for a nuclear quantum effects. A dynamic process also play an important role in elucidating the reaction mechanism. For example, the deviation trajectory and also the standard variational transition state theory are insufficient to describe some general or specific catalysis like decarboxylation of beta-ketoacids. And the quantum kinetic is understanding the electron and also the optical property of some material. So hence, if we continue to ignore the nuclear dynamic, it will hamper the development of a more complete and also predictive framework for our chemical reactions. Thank you.
Another challenge is the chemoinformatics. Data knowledge-driven and the machine learning procedures will merge with computational chemistry methods. Some of the established examples of chemoinformatics are neural network and the machine learning density functionals. Recent applications of chemoinformatics in the context of massive molecule screening were shown as it can be used for the rational design of improved electrochemical energy storage devices and the development of automated schemes for the prediction of degradation processes in batteries. The vastly growing field of the machine learning technologies may only have a big impact for selected computational chemistry problems, especially when the questions and the interactions are fuzzy. Mostly, the rules of engagement are well defined by the quantum chemistry and the statistical mechanics, a situation in which a traditional theory-based approach is probably more successful. Another aspect with room of improvement is the currently relatively loose connection of the fields of quantum chemistry and informatics, and some of the merging here might have a big impact on the efficiency of even long-time used standard algorithms.
Hi, I'm Jiaying. I will present the problems or challenges faced in the field of stereoelectronic and other chemical concepts. The first one is that the stereoelectronic effects are empirically highly useful, but often not backed by quantum mechanics theory. For example, there is no quantum mechanical operator working on the wave function to give partial charges as an observable. Hence, there is a need to improve this and chemical concepts to advance our understanding of chemistry. The next problem is that the covalent and non-covalent interaction integrated in the form of the energy, wave function, electron density have been neglected in terms of empirical or construction of theories. For example, London dispersion, LD, which is usually considered weak, was initially not properly accounted for in density functional approximation B3-LYP formulation. London dispersion should not be ignored as there are structures which exist only due to this interaction. Besides the special treatments of non-covalent and LD, London dispersion interactions will become obsolete in the future because they are integrated from the very beginning into all electronic structure methods. All the argumentative concepts will be replaced by unified and chemically views which are more convincing. Moreover, the renewed energy decomposition analysis for chemical interactions has tendency to be criticized for being unphysical and non-observable. However, the experienced chemists are still able to solve the problems with small interactions and by comparing the trends to obtain a better understanding.
I'll be talking about the development of automated procedures for finding new reactions. The challenges arise as we can discover new chemical reactions on the computer before we carried out experimental procedures in the lab. For instance, the first principles molecular dynamics simulations of chemical reactions is to discover new or known structures and develop chemical pathway. For example, Ab initio nanoreactor was used to probe the outcome of the famous Urey-Miller experiment, and it provides the evidence for novel mechanism for the formation of glycine from basic starting materials. Other than that, the automated generation of reaction pathway from the input of reactant structure and new tools can be used to interpret reactions in mass spectroscopy experiments. So to conclude, these are the 6 grand challenges of computational chemistry theory development. The first one is development of robust and fast electronic structure methods. The second one is seamless and automated multi-level modeling, including the error estimates. And the third one is routine treatments for many nuclear degrees of freedom and entropy. The fourth one is inclusion of solvation effects. The fifth is prediction of molecular as well as the macroscopic bulk properties. The last one is the automated approaches for finding new reactions. Lastly, as a chemist, we need to equip ourselves with constructive input of knowledge of basic theory, chemistry, and chemical reactivity in order for ourselves to make true predictions so that the amount of electrical energy consumption will not be wasted when the predictions are made wrongly.